Okay, welcome back. Today we're going to talk about the surface flow on two-dimensional surfaces, Ricci flow, and develop some of the new techniques that are necessary in that setting. The main point is that in two dimensions we just have the Gauss curvature, so there's no way to compare the eigenvalues of the curvature tensor to each other algebraically. So the techniques essentially have to be all analytic, and in fact this is the first case where we really have to do integral estimates. So let's consider the case on surfaces. So we have some sigma 2 is a closed, smooth Riemann surface. And we have some initial metric there. And then consider Ricci flow. So we have ddt of gij is equal to minus 2 rij. And in the two-dimensional case, the Ricci tensor is just given by the Gauss curvature. So this is minus 2 times, and here we have g 0, 0. So this is minus 2 times g times the metric itself, and 2 times g is the scalar curvature, so we just get minus r times g in this particular case. And of course, this means in particular we remain in the same conformal class as I said last time. So g of t is in the same conformal class as G0. And the other thing, of course, is that because we are in the two-dimensional case, the Gauss-Bonnet formula tells us that the integral of G, and therefore the integral of R, is a topological invariant. So in this case, our little r, which is, so in this case we have integral r du, let's say 2 times the integral of the Gauss curvature of the two surface. So this is 4 pi times the Euler characteristic of sigma. And this means that the area so this is just a constant, and if we then fix the area, the average of R will also remain constant. So such that the rescale flow and so I dropped the tildes here. I just write ddt of gij is equal to, and now rescaling means I just put little r minus capital R times gij. Satisfies sigma t is sigma 0 area. The area doesn't change, it's constant. But in this case, also because the area is constant and integral g is constant, also little r is constant. Okay? And so in this case it will be crucial to distinguish the 3 cases where we have positive curvature, zero curvature, and negative curvature. So there's essentially 3 cases for the Ricci flow on surfaces, r less than 0, r equals 0 and r positive. So the spheres plays a special role, the torus and Riemann surfaces of higher genus. To see how in this room it works with the blackboards. Now, because we are in the two-dimensional case and we stay in the same conformal class, there's an obvious way how to reduce the problem to a scalar equation. Namely, we can do the following, since all metrics are conformal to G naught, we can write G of t equals e to the 2 phi times G naught, or some scalar function phi from the two surface cross time into R. Now, when you have such a scalar function and a conformal factor, well, then our evolution equation for the metric Gij equals minus or little r minus capital R times Gij, if we take the rescaled version, becomes equivalent to saying that ddt of e to the 2 phi is equal to little r minus capital R times e to the 2 phi. Because this has to fit together, and this then can be translated into an evolution equation for phi alone. So this says that ddt of the exponent 2 phi has to be the same as on the right hand side, the like taking the logarithm, so we get ddt of the logarithm is then r minus r, and now we need a formula relating r to phi, but there's a clear-cut formula that you can compute how the curvature of a conformal metric relates to the metric of the to the curvature of the original metric, and it tells you that you have to take the Laplacian with respect to the original metric of the phi minus 1/2 the scalar curvature of the original metric, and then you get the relation to the scalar curvature of the current metric by this formula. Okay? So in particular, if phi is a constant, then obviously you just get the usual formula for rescaling the scalar curvature, but if phi is not a constant, you get this extra Laplacian term. And now, once you have this general formula how to relate the curvature of two conformal metrics, you can then insert this into the equation for phi, and you get the evolution equation for phi. You get on the right hand side e to the minus 2 phi times the Laplacian with respect to the fixed initial metric times phi minus 1/2 the initial scalar curvature, and then you get plus 1/2 r. So this is a parabolic equation because Laplacian is an elliptic operator, but you have, of course, the nonlinearity coming from this factor here. So this is a nonlinear but parabolic scalar equation. controlling the whole thing. Okay? And the other thing we know is just our old evolution equation for the scalar curvature. Right? We knew that ddt of the scalar curvature is equal to the Laplacian plus 2 times Ricci squared. In this case, Ricci squared is just given by the scalar curvature. And if we have the rescaled equation, we also get the term little r. So we have 2 equations that govern the Ricci flow in this 2-dimensional case. Now, it turns out that the regularity theory now is hard because this quadratic term here makes it hard to get an upper bound on the scalar curvature. So just working with this equation alone turns out to be hard to get regularity estimates. We will have to look at the derivatives of R, but in a first step, Hamilton had an idea how to control the long time existence of the flow by introducing a potential. And this works the following way. So, on the potential. Now, since sigma 2 with the metric at time t is a closed Riemannian manifold, no boundary, we can solve the linear problem at each time t, where we put Laplacian of f equals capital R minus small r. We can uniquely solve this provided we fix the volume of f, because this operator has a one-dimensional kernel, which is exactly the constant functions. So to get rid of the constant functions, we have to fix the volume of f, and we just, of course, take the simplest way and ask that the integral is 0, and then we get a unique solution f. Let's solve this with a unique, smooth f. Now, if we can solve this with a unique smooth f for each t, then there should be a unique way how this f propagates in time. The hope is that this f captures some of the properties of the surface, and it may be easier to get understand the evolution equation of f than the evolution equation of r. Now, how do we get the evolution equation of f? We just differentiate this whole equation. So differentiate the equation in time, and then you get on the one hand you get ddt of the left-hand side. Ddt of little r is 0, we know. So we get ddt of capital R, which we just computed as Laplacian of r plus r times capital R minus r. This is the evolution equation from this side. So this is ddt of Laplacian of f. Now ddt of Laplacian of f, we have to work. This is ddt of g upper ij times the second coordinate derivatives of f minus the Christoffel symbols, df dxk, and we just have to do it. So this is the inverse metric and the inverse metric has the other sign in the evolution equation, so this is equal to capital R minus little r times g upper ij times this is just giving us back the Laplacian of f. Then I have to differentiate the f here. If I differentiate the f, then I just can insert the evolution equation, I just insert ddtf, and what I get is the Laplacian of ddtf, which is good because we want to solve for ddtf, we want to know what this is, but we get an extra term from the Christoffel symbols. Now if you differentiate the Christoffel symbols, you get minus g upper ij times, and then in there you get the derivatives of the, it's all derivative terms of the metric, and so you get gradient Ricci in here, and the terms that you get are minus, well, there's one plus term, so this is gradient I rjk, and it was 2 times Ricci, so it cancels against the 1/2 from the Christoffel symbols, and then there is a gradient j rik, and then there was a minus sign, gradient k rij. Yes. And now notice that by the contracted second Bianchi identities, this term gives gradient r, but all of these two traces give 1/2 gradient r, so these cancel perfectly out to 0. So this term goes away. And so even though I forgot that we have the xk, so this term will be 0. So now setting this up to putting everything together, we get that Laplacian of ddtf is equal to, let's see, I get Laplacian of r, and this one I write as r times Laplace f, because r minus r is Laplace f. But then from this side I get a minus r times Laplace f, and then I get from here a plus little r times Laplace f. So these two terms cancel, and the whole thing ends up as Laplacian of r plus r times f. But now we have a Laplacian of this is equal to the Laplacian of something else. And therefore, then the two things that I take the Laplacian of must coincide up to a constant. So I get that ddt of f is equal to Laplace is equal to r, and r on the other hand, I could have just written Laplacian of r minus little r, so this is Laplacian of f. Right here I could have written Laplacian of capital R minus little r, which is the same as the Laplacian of f, plus r times f, minus some constant that may depend on t. So now I still have to find out what this constant is. So I got this equation, and I just have to find out what this constant is. Now, to do that, let's first take the original equation Laplace f equals capital R minus f multiplied by f and integrate. Then you get R minus little r is this. And integrate, then you get minus integral gradient f squared on the left hand side. And on the right hand side you get integral of capital R times f mu, because little r times integral f is 0 because r is a constant. So noticing this, and on the other hand we want the integral of f to remain 0, so we know that 0 is equal to ddt of the integral of f, which we can now compute from our evolution equation. So we get integral of Laplacian of f plus r times f minus b of t d mu, and we get also from the volume element, we get plus integral f times r minus little r d mu. Little r minus capital R d mu from the volume element. And now integral of Laplacian f is 0, integral of a constant times f is 0, so this is just minus b of t times the area, and then integral of f times little r is 0 because little r is a constant, and minus r times f we have just computed to be integral gradient f squared. So this allows us to solve for b of t. That's the integral of gradient f squared d mu divided by integral d mu. So it's just the average of integral df squared d mu. And we get the evolution equation finally that ddt of f is equal to Laplace f plus r times f minus the average of integral df squared. Okay. The nice thing here is, of course, that this is essentially linear in f. So f has a nicer evolution equation than the scalar curvature r. Now, the next idea is we want to understand the scalar curvature. Now the scalar curvature is Laplacian of f. So let's look at the evolution equation of Laplacian f using the evolution equation of f. And the observation that Hamilton made was you should not just look at the Laplacian of f, you should add gradient f squared, because that gives you this good Brochner term that magically combines with the other terms and gives us a good evolution equation. So, consider the quantity h is equal to the Laplacian f plus gradient f squared. And then we compute the evolution equation of h. Now, ddt of h, since Laplacian of f is scalar curvature minus little r, and little r is constant, this is the same as d dt of r, the first term, plus d dt of gradient f squared. Now the gradient of f squared, we have to think of, again of d dt of the metric and the evolution of f. So here we write this is Laplace of r plus r times r minus r, right? This was our evolution equation from here, which we formulate in terms of h in a moment. But then from here we get some extra terms. So we get from the g upper ij we get a r minus r times gradient f squared. And from here we get two terms which look like di f times gradient j of and then we insert the evolution equation of f, which is Laplace f plus rf minus b. And now Laplace of r is the same as Laplace of f, and r minus r we write as Laplace f squared. Here I made a mistake because I didn't subtract the little r, so I put the little r back in. So this is little r times Laplace f. And then we have here plus r minus r gradient f squared. And in this last term here, if I replace, well, first of all, there is plus 2 little r gradient f squared. The b term goes away because it's a constant. And then we get from here, if I exchange the Laplacian with the dj, I get on the one hand Laplacian of gradient f squared, and then I made the mistake here from the two derivatives from the Laplacian distributed, so I get have to subtract minus 2 times the Hessian of f squared. And then the other thing I did was I exchanged the Laplacian with the gradient, so I get the commutator term, which is a Ricci tensor. So, and the Ricci tensor is given by the Gauss curvature times 2 gives me scalar curvature, so I get a minus r times gradient f squared from this commutator term here. And now I should have it right. So collecting everything, I have the Laplacian of f, let me see, Laplacian of r. The Laplacian of r is, oh, that's the Laplacian of the Laplacian of f. Right, Laplacian of the Laplacian of f. And on the other hand, I have the Laplacian of the f squared. So this together is the Laplacian of h. And then I have the r df squared with a plus sign here with a minus sign there cancels. And I have that the here's a 1 minus r df squared, and there's two pluses, so 1 remains, so I have plus r df squared. And then I have plus r Laplace f. This combines with df squared to h, so I get an r like times h. And then I have this term here, minus 2 times the Hessian of f squared plus Laplacian f squared. But the Laplacian of f is exactly the trace of the Hessian. And we are in 2 dimensions. So this here is exactly the trace part of this tensor. So these two combine and give me just minus 2 times the trace free part of this tensor squared. So I can write the whole thing as Laplacian of h minus 2 times the tensor, let's call this mij squared, plus r times h, where mij is the trace free part. So let's collect everything. And then we get a lemma that this quantity ddt of h satisfies Laplace h minus 2m squared plus r times h, where mij is equal to the tensor the Hessian of f minus 1/2 the trace of the Hessian times gij. Okay. And that's magic, that we have sort of this is a magic observation from Hamilton, that we get this negative term here and something that's just going linear. And this gives us an upper bound on the scalar curvature, because little r is a constant, doesn't change in time, and the leading term in h is the Laplacian of f, which is the scalar curvature minus little r, and the other term is positive. So we get an upper bound on the scalar curvature from this identity, and that's a key point for the long-time existence. Right, so this implies by the maximum principle that h is bounded from above by the maximum of h on the initial surface multiplied times e to the r times t. And this implies, of course, that the scalar curvature, which we know is bounded from below. Yeah, I didn't say that, but ddt of r is equal to Laplace r plus r times r minus little r. So even so if little r is negative, then it's clear that it's growing. But even if little r is positive, this will be bounded from below. So And the key thing is the upper bound, and since h is equal to since right, we have h is Laplacian f plus df squared, which is equal to r minus little r plus df squared. So this is bigger than capital R minus little r, and little r is a constant. So we get that capital R is less than this constant here, the initial data, times e to the r times t plus the little r. So we have a uniform bound on the scalar curvature, and this gives us long-time existence, because we know once we have a bound on the scalar curvature, we get all higher derivatives bounds on the curvature, and then we can always extend the flow a little longer on each time interval. So let's collect this. So we have a theorem. There's two parts. First of all, for any, in all cases, the rescaled Ricci flow on surfaces has a solution for all positive times. Okay, so we have a solution for all time. Then the second thing is that in the case of negative curvature, so if r is less than 0, then the solution converges exponentially to a metric of constant Gauss curvature. Constant negative Gauss curvature. Okay. Now, concerning the proof, one is we know from bound on R get all higher derivatives. This was a very general result we proved, and then we get also the Christopherson books bounded, and the metrics are all remain equivalent to each other on finite time intervals. But this is enough to prove long-time existence. For the second thing, you notice that if R is negative, then this term is decaying fast, exponentially. And similarly, you can show that if R is less than 0, you get that, in fact, from the evolution equation of R, that R converges also from below exponentially to little r. Converges to little r exponentially. But then this means in particular that the time derivative of the metric decays exponentially. Exponent, and then you get also all the higher derivatives converging exponentially, and you get convergence. So that's the simplest case. Slightly harder is the case where r is equal to 0. Now, in the case r equals 0, the simplest way to prove it, but also a little bit awkward, is to just use the uniformization theorem. You know, if it's r equals 0, the metrics on such a Riemann surface are all conformal to the flat metric, so you just pick a flat background metric. Simplest approach. By uniformization, there exists some background metric G0. This is not the initial metric, maybe I should call it G bar, flat, such that the metric G of t is equal to e to the 2 phi times G bar, and then the evolution equation is independent of which background metric you choose. So we use the evolution equation that I proved at the beginning of this lecture. And since it's a flat background metric, most terms drop out. The only term that's not dropping out is the Laplacian with respect to the background metric. And the other terms involved little r, which is 0 because we're on the torus, and involved the scalar curvature of the background metric, which is by assumption a flat metric, is also dropping out. So you get this a simple evolution equation for phi, which means by the maximum principle that phi remains bounded above and below. Phi, so phi is bounded above and below, which means in turn that the conformal factor e to the 2 phi is bounded between two positive constants. But if the conformal factor is bounded between two positive constants, it means all the distances, injectivity radius, volume, and so everything is bounded above and below. Diameter, Sobolev constants, Poincaré constant, all bounded. And once you have that control, it's not hard to see that you prove integral estimates on phi and get all higher integral estimates. Get integral estimates on all derivatives of phi, and this gives you the result. Now, if you want to have a cleaner proof, nice more geometric proof, you could go to the original paper of Richard Hamilton, or you could go back to our evolution equation for little f and little h, and these become nicer as well. In particular, for example, the evolution equation for h only has this negative term on the right-hand side, and you get a slightly cleaner proof if you do it that way. Okay, now the really interesting case, the really hard case, which requires new techniques, is the positive case. In particular, the case of the sphere where the initial metric is of positive Gauss curvature. The general case where you have an arbitrary metric on the two-sphere was later settled by Ben Chow. So here's the, we are now going to the case r greater equal to 0. And in this case, the theorem 1 was due to Richard Hamilton. If, in addition to the average of the Gauss curvature being 0, the Gauss curvature, the scalar curvature, is strictly positive everywhere on G0, which is then, of course, preserved by the flow, then the flow, the Ricci flow, converges, again exponentially fast, to the metric of constant Gauss curvature. And the remaining case, which was proven by Ben Chow, for any G0 with little r greater than 0, same result. And but this theorem just traces back, uses the techniques from here, and reduces the general case to the previous case. So we will concentrate now, because it's slightly less messy than this, concentrate on the proof in the case of strictly positive scalar curvature. And the problem is, here's the thing we are worried about. So we know already we have a long-time solution, so you may think, what can go wrong? We have a long-time solution of the flow. We know it has positive Gauss curvature. What on earth could go wrong with the solution? Here's what could go wrong. So the problem is that we don't have an upper bound. Do not have an upper bound yet on R independent of T. That's the problem. Geometrically, it means we are worried about the following picture. We know the volume is constant. So here's this two-dimensional metric, somehow represented by a surface in R3 to make it look like. And the worry could be that although the total area of the surface remains the same, that during the evolution it could develop into something like this. Something huge, long, which completely deteriorates, always having the same area, but getting more and more along such an elongated solution. Now we know there's a solution forward in Ricci flow, which comes from infinity, the so-called Rosenau solution. I think I mentioned it at the beginning, which comes from sort of something which initially looks like that and then shrinks to a sphere. But we are worried now that, but even though we fix the volume, that for some reason the thing deteriorates like this. And this is a basic problem in Ricci flow that has to be overcome. Also if you think of higher dimensions, because if you want to prove the Poincaré conjecture, 3 dimensions, you're worried about these necks forming, which look like a 2-dimensional surface cross R. Now if this neck deteriorates in such a way, then we will never be able to do any surgery and overcome the singularity that happens in the 3-dimensional case. So before we have any chance to understand what happens in the 3-dimensional case, we first have to understand what is happening on S2. And this is the basic problem that somehow has to be dealt with. And it turns out the technique is we have to somehow show that if the curvature gets huge somewhere here, it cannot drop off fast. You see, if this picture happens, then we have huge curvature here and then much smaller curvature there, because here it looks like a cylinder and the curvature is very close to zero. So the idea is to show that the curvature does not drop off too fast from here to there. Now the easiest way to do that would be to prove a gradient estimate for the curvature. So this is what Hamilton told me he tried to do. He started from the evolution equation for R and tried to prove an estimate for the gradient of the scalar curvature. Now that didn't work, so he went to the second derivatives of the scalar curvature, and he found a magic cancellation between certain evolution of second derivative of scalar curvature and first derivative of scalar curvature, and that led to the so-called Harnack inequality. So technical tool that we're going to use, a Harnack inequality, for the scalar curvature. And this will be the topic of the next lecture. Thank you, till next time.